Hello everyone and welcome back to another episode here of the Hidden Quantum Champions on the Polaris School of Quantum. Today we are looking at a company called Alpine Quantum Technologies, short for AQT. And without further ado, let's hop right into it. Let's go to their website and see what they are doing. So here we are on the website of AQT. It says the home of ion trap quantum computing, Innsbruck, Austria. And I think it's fair to say that Innsbruck is probably one of the main spots here in Europe for technology development in ion trap computing, or generally in ion traps, ion trap manipulation, and then of course also quantum computing based on that. AQT realizes the first general purpose quantum computer. There's some information with read more, and in the background I think what we are seeing is the ion trap. So here we see this optical table down here, and there are some fibers I think connected over here and some cables. So I guess that's where like the quantum computer is actually being located in. Let's scroll further down, and here it says innovation, future, turnkey quantum. Leverage our quantum computer to tackle challenges in finance, chemistry, logistics, and beyond. So here we have, let's say, the magical triangle again. So finance, chemistry, and logistics as use cases. And it goes on to say we offer fully functional trapped ion computers ready for integration into existing high-performance computing, HPC, data center installations, and cloud accessibility. Our entire quantum computer requires only 2 full custom 19-inch racks, runs in a comfortable room temperature environment, and consumes less than 2 kilowatts of power. And I think these are all very important benchmarks. So looking also at competitor solutions, especially from some players in the industry, these 2 racks are actually quite small. There are also other quantum computing manufacturers in the realm of ion traps that make smaller solutions, but let's say in the past these solutions used to be actually quite big, and that's because you have all of these lasers, all of the optical components, and that just needs a lot of space, right? So 2 19-inch racks I think is comparatively small considered. You don't need any, let's say, cryostat technology like in the solid state cases, and 2 kilowatts of power is also not extremely much. It is something that in a data center you can make available, right? Then going on here to the solutions. So possible uses for quantum computing, research, industries, and public authority. And I guess if we click on them, we can also learn more about each single one of them, but we will keep that for later. So our quantum computer, the world's leading 19-inch rack-mounted quantum computer. Here we see it. It's in a black box, which says AQT on it. There we see some electronics up in there. And then I guess there's some optical components as well. So probably these are cables and some fibers for the control. It says AQT's quantum computer is characterized by its innovative and proven architecture, as well as its modularity and expandability. The system has demonstrated the highest quantum volume in Europe so far, and applications in numerous quantum computing use cases. Furthermore, the system operates at room temperature and consumes less than 2 kilowatts of electrical power, eliminating the need for special cooling, water, or extensive energy infrastructure. So, why do they actually say that? Let's go from the beginning. So, characterized by the innovative and proven architecture. I guess we will learn a little bit more about the architecture later on. Then it goes on to say highest quantum volume in Europe. Now, a quick word on the quantum volume. You might have heard earlier in this series the comparison to Moore's law, and there are people that say that a similar law applies in quantum computing. Different people have different names for it, but at the end, so Moore's law is basically saying that the density of your transistors on a classical chip, as in today's computers, is increasing. So it exponentially increases. So that's why we've seen all of these technological developments over the last decades, going all the way to smartphones that have now a computing power higher than what actually got the first man to the moon. So that's the story about classical computing. And now some people are saying, okay, the same is true for quantum computers. The number of qubits will scale every year or every 2 years will double, whatever. There are different versions of that. And this could potentially even be true, but actually it's not only about the number of qubits, because in order to really make use of those, you have to be able to not only bring every single one of them in superposition, but also to be able to entangle all of those. So there are other metrics that are playing a role as well. You can easily create a chip with, spin qubits with thousands of qubits on there in theory. But practically, it's kind of hard because first of all, you need to cool it down. So there's a different issue there, which is the cooling issue. And then secondly, and that's because you have all the control lines. And then secondly, you also need to make sure that the fidelity, and that not only applies to spin qubits, but to all qubits, right? That the fidelity of your gates is high enough so that you're not accumulating too much errors. And then you also need to have an error correction protocol running, because even if your fidelity is high, you might still collect errors due to cosmic rays, for example. And there's also publications on this. So what I'm saying with that is, it is not only about the number of qubits, it's also about the number of gates and so on. And actually combining this into one metric is what kind of the quantum volume or the accessible quantum volume is referring to. So it is basically how well can you actually entangle your qubits, use them for operations within the Hilbert space, which is where, let's say, the mathematics of the quantum theory is happening, which is what gives the quantum computer a boost. So how well can you actually use the quantum properties to perform your calculations, your emulations, and so on. So that's the quantum volume. It is a metric that is derived out of multiple different metrics that quantum computers are accessing. Now, it goes on to say these things about room temperature, and that's compared to, for example, cryostats that need to have this whole complex cool down procedure with liquid helium and helium mixture, right? So that's not needed for those ion traps. Then it says it consumes less kilowatts of electrical power. That also refers to all of this complexity that comes with the cooling systems, with ever bigger cooling systems if you want to have more qubits on a chip. And then you see here the special cooling, like cooling water, for example. That is also an issue, right? So you have this mixed helium which you need, but also on top of that, you need to have a cooling water supply to actually cool the compressor that is driving this helium. So there's a lot of more complexity, which they say in their system with the ions you don't have. So less extensive energy infrastructure as well. Now we move on down here. So I guess that is the ion trap. So you see these quadrupole set up with 4 different gates that you can use, or that you can electrically bias, and thereby using a dynamic field, you can basically trap the ions within there on a linear chain. So they will sit here in the middle, one after the other, like one to the next in a 1D configuration. At least that's my guess looking at this. I'm not an expert though in ion quantum computers. That's just what I know. So experience high performance hardware, speed up and increase the performance of your research using Pine setup, the leading modular trapped ion architecture, Beach, perfect for laser stabilization in demanding applications, and Rowan generation and full control of laser light pulses. And there's of course more information on that as well. Then we have the cloud access, and that's also something that we've seen with other competitive technologies or companies as well. So instead of just selling the hardware itself, which is quite expensive, so a quite high entry barrier, they also have this cloud availability where you can get cloud access to a quantum computer and therefore have an easier entrance into the product. And here it says deploying your algorithm through our Arnica cloud service. So that's the one that we see here, Arnica, the cloud service to their AQT computers. So it says access to AQT's latest quantum computers and simulators, providing you on-demand, high performance and reproducible quantum computing with a universal gate set. quantum computing opens up novel possibilities for algorithm design. Quick note on the universal gate set, so that's also something to note here. Not everything that is marketed as a quantum computer or a quantum simulator has a universal gate set. The universal gate set is similar to what you have on classical computers. It is a set that enables you, or that maps basically to all the relevant mathematical operations. If you don't have that set of gates, you cannot actually do all types of mathematical operations, and with that you cannot actually implement all the relevant algorithms. So not every application can actually be mapped onto what the system can perform. And the quantum computer, as we are talking about it today, is a system that has a universal gate set. There are also other systems that are using properties of quantum mechanics, like, for example, the famous machines from D-Wave that we know, let's say the original generations. They're also looking into universal gates now. And if you haven't watched the video, make sure to check it out in the playlist on the Hidden Quantum Champions. But so there are machines that don't have that and that cannot access, or that cannot actually perform all types of operations. There is a quantum SDK, so it says quantum SDK software development kit, right? Connectors for Anika, simple integration with industry standard quantum software tools and workflows is realized with dedicated Anika connectors for various quantum SDKs. And I guess that refers to all the different programming languages like Qiskit, for example, which is a pretty well-known one. Then you also see here quantum simulator for AQT quantum computers. Get started easily offline and for free. We offer high quality offline simulator for prototyping quantum circuits and algorithms and exploring their performance under realistic environment conditions, which makes porting code to your quantum computers seamless. To our quantum computers seamless. So a simulator that not only simulates the actual gate, but that actually simulates the properties of such a system. Now, what is meant by that? I guess that also refers to things like fidelity of the gates, maybe, but it also refers to things probably like what is the actual setup of the quantum computer, because oftentimes in the theory you can just connect every single qubit with every other one. You can apply Hadamard gate or whatever to whatever qubit you want, but in the reality it's oftentimes the case that you cannot connect every single qubit directly with each other. Like, think about all of them sitting in a one-dimensional chain, right? Now it might not be so easy to connect a qubit that is on one side of the chain with one that is on the other side of the chain, and then you have to go via some let's say intermediate interaction to actually couple those with each other. And I guess that something like this would also be mapped here in this simulator. And then finally, examine the API documentation of the Anika interface. Enjoy seamless integration by obtaining direct access to Anika without the need for an SDK connector. Finally, there's some news down here. So you see the news section. It says we had the honor of welcoming the President of Germany, Frank-Walter Steinmeier, and the President of Austria, Alexander van der Bellen, to AQT. We had the honor of welcoming, it's the same thing again. Then there was an inauguration of PIAST-Q, a leap for European quantum computing, and there's more news down here. Leading the quantum evolution, so AQT realizes the first general purpose quantum computer. The system is the first commercial 19-inch rack-mounted room temperature quantum computer. Use our quantum computer via the cloud to solve challenges in finance, chemistry, and logistics. We've read that before. Finally, there's something about them, the product, and of course the careers page. Finally, there are some information here about the partnerships. So as many other players in this ecosystem of quantum technologies, also AQT has a partnership with different companies from the space. So for them, as a hardware provider, I guess it makes sense to talk to, for example, the software providers. You see, for example, HQS Quantum Simulations here, Riverlane, Multiverse Computing. So these are all names that are known in the quantum universe, and some of them have also been covered already within the series. But you also see company like T-Systems, which is part of Deutsche Telekom, I guess, as a potential customer, I guess, because they are also operating, let's say, cloud systems, server racks in their data centers, and that's of course where also these machines here would go. So at AQT, we believe that partnerships are crucial for accelerating quantum impact and developing solutions for critical problems. Our commitment to ensuring that our customers benefit from cutting-edge technology drives our collaborative efforts with leading industry partners, and that's the ones that are mentioned here. There's more information as well. Finally, it says we are working on general purpose ion trap quantum computers that will support a broad range of application in various industries, AQT. And as per usual, you see links to the social media and some more information down here, which includes that they are based here in Innsbruck in Austria. Okay, with that, we go all the way up again. We are looking into the products now. So there are different products that are being mentioned here. One of them is the quantum computer. That's something that we've seen already. There's the cloud access, but also the components. So the strategy is also to sell, let's say, the components that make up the quantum computer to, I guess, research labs that are interested in building their own. So here it says quantum computer, components, cloud access. We already enable our customers to install trapped ion quantum computers on site or to use them via a convenient cloud solution. AQT supports research customers with quantum hardware components and complete solutions that significantly accelerate the development of quantum optics experiments. Scroll down or filter to find your perfect match. And here we see now, I guess, the first quantum computing system on their website, the first commercially available one. It's called Merit, and it says the first commercial 19-inch rack-mounted quantum computer, which has 20 qubits, which are fully connected with each other, so you can connect each qubit with every other one. It has a quantum volume of 2 by the power of 7, so 128 quantum volume on a 7-qubit register. If you are interested in, let's say, learning more about the quantum volume and what is actually like an accessible quantum volume, I can definitely also make a dedicated episode about that. Let me know down in the comments below. There's some information here on the single qubit gate fidelity and 2-qubit gate fidelity, which are also metrics that we've seen before. So for single qubits, we are talking about 99.96, and then for 2 qubits, 98.47% of accuracy, fidelity. And what is very interesting here, they also explain how it's measured. So it's 2 qubit gate fidelity over all pairs on an 11-qubit register. And they also say the, let's say, tolerance here, which I haven't seen actually with many others yet, which probably caters to the very scientific approach that they are also following, as in, well, I mean, all of them are scientific, right? But this is like what you also learn in the lab courses in physics when you are studying physics, that you always need to add the accuracy information. I've seen that with the particle physicists a lot as well. So whenever you have statistics, right? And here you can do statistics. So then we also see here the IBEX Q1, our quantum computer system that executes your quantum circuits via cloud access. So that's the system that sits behind the Anika cloud, which has 12 fully connected qubits, a little bit less than this one and a little bit less than the Merit, at a similar, which even an equal quantum volume. And then again, you see here the gates. It even has a little bit higher single qubit gate fidelity and a slightly higher 2-qubit gate fidelity as well. Finally, we see here the component section now. So this is the Pine trap. That's what I mentioned before, right? This is an ion trap, high performance ion trap for quantum applications. You see here the benchmarks. I will not go through them. I can anyways not add much information because I'm not an expert when it comes to these traps. Then you also see the full setup here. So that now also includes the vacuum chamber, I guess the optical access points and so on, which like all the peripherals that you need around the actual trap to actually isolate ions and optically access them, right? So here you see modular trapped ion architecture for your quantum applications, or four optical fiber ports, 2 different species possible. So that's, let's say, the full setup as it would go onto your lab table. And then there's speech compact frequency stabilization unit with ultra low long-term drift, typically below 25 kilohertz, and so on. Then there's Rowan. We've also seen, I think, that before. It's a compact and rack integratable module for generating and controlling laser light pulses. And you can really see, and it has a spectral range from 400 to 900 nanometers, which I think, again, is a very typical range for the, let's say, typical types of ions that you are looking at. But again, I'm not a super deep expert on that. But what I can see here is, if I look at this, so this is very compact, I think, for an ion trap. So I've seen things that are much, much bigger, or that have much more, let's say, connectors and stuff around them. So that looks very compact. And if I look at these, also this one looks like it can be rack mounted. I think it said also in this one here that it's rack mountable. So if you look at these components, I think they actually look exactly like they would fit in here. So I assume that like what they are selling here in terms of single components for the research, for the R&D, is the same type of technology that they are also using in their production type of systems. Then there's also some information here about Annika again, remote access to our iBags quantum computers, unaltered processing of native gates, reliable reproducible quantum computing, European made and hosted, and then quantum SDK integrations available. So these are the products. On the solution side of things, I think we've heard it before, right? So there's the research side of things, public authority side of things, and then of course there's also the industries, and the industries include the 3 ones that we've heard before. I would assume if I scroll down here, I see them again. So if I go to industries, you see this is probably finance here, simulation, so aerospace. Then we have here simulating material properties, which I think is something that feels very native to quantum computers. So using quantum computers to emulate, simulate quantum property of a material. And I mean, there really the material properties are guided or are governed by the quantum mechanics that is below them. And it makes sense to use a quantum computer for that, from my point of view. But there are also different opinions on where the quantum computer can generate the biggest benefit. And then there's other ones here, like the manufacturing industry, the molecular simulation. So that goes into the direction also, I guess, of pharma industry. But it also mentions hydrogen here, for example. And then there's integration into a high performance environment. I guess that is more like, okay, their solution fits into what people are requesting in HPC. And then there's also something here, you see Covestro, for example, and Boehringer Ingelheim, so that goes also in the direction of pharma and chemical. And public authorities, so from the lab to the data center, and let's say very similar things that we've seen already before mentioned here. With that, let's quickly also check out about the company a little bit. It says Innsbruck, Austria, the home of ion trap quantum computing, and here we see a very nice setup with like the Alps in the background, the green fields here, and the computer sitting on there, and a lady smiling at us with, I guess, a laptop maybe or a notebook in her hand. It says bringing together more than 6 decades of experience in cutting-edge research on trapped ion quantum technologies, we have teamed up to realize the world's first general-purpose ion-trapped quantum computer. AQT already enables its customers to either install quantum computers on-site or access them conveniently via our cloud solution. We support customers in research with quantum hardware components and complete solutions that significantly accelerate the development of quantum optics experiments. Values of the company are mentioned here. So it says passion, teamwork, and family-friendly culture. We make European quantum computing superior and more readily available for international customers. All components of the AQT quantum computer are engineered to fit within 19-inch rack cabinets, allowing familiarity to existing high-performance computing, HPC infrastructure, and data center installations, empowering a robust quantum ecosystem and driving holistic acceleration. We make advanced technology effortlessly accessible through seamless cloud integration, says Dr. Thomas Mons, the CEO and co-founder of AQT. Here's a quick overview on the achievements that they have had so far. So the founders of AQT have been the first persons to realize a controlled NOT gate operation, the building block of general-purpose quantum computers. Since then, ion trap quantum computers have been at the forefront of quantum technology development, from atomic clocks to quantum simulators to universal quantum computers. And here we see some of the major milestones. So 2011, which is more than 10 years ago, was the world record on 14 particle entanglement. So I guess they had 14 ions sitting in a trap and they managed to entangle them, probably via some vibration mode or something like that. Again, I'm not an expert on that. 2014, still more than 10 years ago, topologically encoded quantum error correction. Then in 2016, realization of a scalable Shor algorithm. So Shor algorithm, just quickly as a reference, is the algorithm that is being used for prime factorization. Prime factorization is when you have a number and you divide it into the prime numbers that you have to multiply to each other to get that number. For example, 15 is divided by 3 equals 5, and 3 and 5 are both prime numbers. And this is actually an important algorithm which is being used in today's encryption. So the encryption idea is that you have an asymmetric problem. Why is it asymmetric? Because if I give you some arbitrary number, like for example 21, then it's kind of hard to figure out what are the two components multiplied by each other that are prime numbers that are giving you 21. Well, for 21 it's easy, it's 3 and 7. But if you now go up to higher numbers, this becomes more complex. On the other hand, if I tell you, for example, the number 3, then it's kind of easy to figure out the other one. It's 7, right? So you just have to do a division operation, while for the other ones you have to test out all the combinations of factors until you end up at the correct pair. And that is something that can be used for an asymmetric encryption scheme. So you can basically share some information with somebody else and easily encrypt, but only difficultly decrypt the message. And that's the idea behind prime factorization. That leads into this RSA encryption scheme, which a lot of today's encryption is based on. And if you now had a quantum computer that could run this Shor algorithm at a very big scale, you could basically decrypt a lot of messages or all messages. And that's kind of leading to this idea also of quantum safe encryption. And if that's something interesting to you, please let me know in the comments below. I will make a separate video on that as well. Quickly going on here, 2018 quantum chemistry calculations. So this is now 7 years ago, actually February 2018, as it seems here from this point, quantum chemistry calculations. So running actual problem calculations on a quantum computer. Okay, 2018, February 2018, and that's, I guess, the milestones that lead to the founding this company, because here it says 2018 Alpine Quantum Technologies GmbH was founded in February 2018 by Professor Rainer Blatt, Dr. Thomas Mons, and Professor Peter Zoller. AQT is developing the first general-purpose quantum computer based on ion traps. And here you see the three gentlemen that have co-founded this company. Then also in February 2018, you see here all the different institutions. The research promotion agency FFG and the University of Innsbruck are investing a total of 10 million euros in the startup company AQT. So that was, let's say, the seed investment. Then you see here the World Economic Forum in 2020. AQT awarded by World Economic Forum. AQT was selected among hundreds of candidates as one of the World Economic Forum's technology pioneers. The World Economic Forum announced its selection of over 100 of the most promising technology pioneers of 2020, who are shaping industries from agricultural to healthcare while also working on sustainability issues and more. Then 2020, we see here AQT computers support 4 SDKs, which is Qiskit, Cirque, PennyLane, and PyCat. Here we see the Iron Trap before, so launch of the Pine Trap available as a standalone Iron Trap module or as research accelerating experimental assembly. The Pine Trap features low micromotion and low heating rates already at room temperature. Here we see the setup from before. Then we come to the Pine module. All the way to IBEX, which is the system that you can access in the cloud, which we've seen before. Then it says quantum volume 128 has been reached. Then in 2023, we see quantum computer for the Munich Quantum Valley. So that's, I guess, one of the first or maybe even the first customer then. 2024, July, a hybrid quantum computing infrastructure for Innsbruck. Together, the University of Innsbruck and AQT have successfully integrated a quantum computer into a high-performance computing environment for the first time in Austria. This hybrid infrastructure of supercomputer and quantum computer can now be used to solve complex problems in various fields such as chemistry, material science, or optimization. AQT selected vendor for the European HPC, so there's the European supercomputing or high-performance computing contract happening, and apparently they are also playing a role in that. Then AQT delivers the PySQ in 2025, June, and I think we've seen some news on that also in the earlier page. It says delivers the PySQ quantum computer to hosting site, Poznański Centrum so the supercomputing center in Poland for the Euro QCS Poland Trapped Ion Quantum Computer, partnering with Euro HPC JU. The official inauguration even took place on the 23rd June 2025. Then we see here October 2025, we are honored of welcoming the President of Germany, Frank-Walter Steinmeier. That's also something we've seen. Then we see the founders and the advisory board down here. And I think with that, we are also already at the end of today's episode. If you liked it, please make sure to give the video a like. And don't forget to subscribe to not miss out on the next one. Hope to see you by then. And as always, make sure to stay hydrated. Bye-bye.